So picking up where we left off, as I mentioned yesterday, sine and tangent are probably the two to know. Cosine is just the negative of it, right? And then something I saw written in my notes I didn't write down yesterday, and you might want to. Arc sine. I know some people yesterday were very much like, wait, I don't remember that. But remember that when we talk something like arc sine, so if it says arc sine of x, that is the same thing as y equals sine inverse of x. Okay, so if you haven't written that down, you might want to write that down to have it someplace in your notes. But other than that, I'm ready to head to part C. Let's practice using those formulas. So C, y equals arc cosine of x squared. And in relation to what I've just said, arc cosine of x squared, another way of saying that is, that's equivalent to saying cosine inverse of x squared, right? So that is helpful to you there. Okay, we're asked to take the derivative. So for the derivative of y, I'm going to write dy dx. Okay, what's my rule for cosine inverse say? If you recall on top, I just kind of thought of it as a negative one. Notice it says negative u prime. That u prime represents the chain rule. Okay, so I'll worry about the chain rule here in a moment. Over, and then what is it? It's the square root, right? I've got to remember mine, sorry guys. Of 1 minus, now, it's listed up top as u squared, right? What is my u value here?
X.
Right. So, little side note, in place of u is x squared. So this is going to be what? X squared squared. Okay, whatever you're putting in there, you're squaring. And then there's filling in your form for derivative of cosine inverse times what? The derivative of the inside. The inside is x squared, so the derivative of x squared is 2x.
How can you just put the negative on the top and on 2x at the top?
You can. I'm getting ready to do that right now. Okay. You can go ahead and do that. That's fine. I was just going to do it now. So, because on top then, that 2x go on top, so it's going to be a negative 2x over the square root of 1 minus x to the fourth. If I had to guess, yeah, that's how it's left in my answer key. Okay. Okay, let's try D then. Y equals sine inverse of x squared minus 1. So, dy dx. Are you working on memorizing these rules? Rule for sine inverse. I guess I think of it as the rule is just 1 over something, and then the chain rule ends up going on later on top. I guess that's why my brain does it that way. So 1 over the square root of 1 minus, now, what's it supposed to be?
X squared minus 1.
Right. So we're going to be doing, in place of my u, it's that whole expression, x squared minus 1. So this is going to be x squared minus 1 quantity squared. And then times
2x.
derivative of x squared minus 1 is 2x. Cleaning this up, I would move the 2x to the top if you haven't already put it there. In that denominator, okay. There is a small bit of canceling if we go ahead and multiply that out. Okay, so with that in mind, I'm going to do just that. It's 1 minus, and it's minus the x squared minus 1 quantity squared. So when you do x squared minus 1 squared, we're going to have to FOIL, right? So x squared minus 1 times x squared minus 1 is going to become x to the, excuse me, fourth. And then it's a minus 1x squared and minus 1x squared, which is going to make it minus 2x squared. And then minus 1 times minus 1 is going to make it a plus 1. Now, I went ahead and left that piece in parentheses, but when we clean up, notice what happens. It's going to become 1. When you distribute the minus, it's going to become 1 minus 1, yes? So 1 minus 1 will cancel. I'm left with negative x to the fourth plus 2x squared if I distribute that. Okay. Well, I'm fine with this to an extent. I'm going to show you a little bit more. Okay. And again, the more you know, the more you can kind of understand when you see something in AP. What do you notice inside my square root sign? There's exponents. What do they have in common?
X.
X to the second. So underneath my square root, I'm going to factor out an x to the second. And then I'm going to be left with negative x to the second plus 2, if you will. Right? Now, the reason I do this, and I factor that x squared out, is because x squared is a perfect square. Like, I can't do anything with this negative x squared plus 2. It's going to have to stay under the square root. But what's the square root of x squared? X, right? And so what can happen here is that x can go out front. Now, there's a little trick here. You're going to see the x in absolute value if you look at something official here. Okay? Reasoning for that absolute value. What do you know about a number that's under the square root sign? It has to be positive, right? So if we're taking the square root of x squared, that x value would have to be positive. And so you'll see absolute value there. And because it's absolute value there, I don't think, yeah, I'm not going to cancel the x on top and bottom. Okay, so you kind of have to be careful there. But, again, I'm not opposed to this answer back here. I wanted you need to see, though, what are some options? What are some things you might see pop up, for instance, on multiple choice? Okay. Questions there? Okay. E. Y equals tan inverse of cosine x. So realizing cosine x is my inside now, isn't it? When we talk about what is u is cosine x, right? So dy dx equals, but what's the derivative of tan inverse of something according to my notes? And it says u prime at top. Realize that represents the chain rule. So 1 over 1 plus, it says u squared. What am I going to use? Cosine x squared. So I'm going to write this as cosine squared x, if you will. Okay, and that's because I'm using u as cosine x times What's the derivative of the inside?
Negative sine.
Derivative of cosine x is negative sine x. If I clean this up, I'm seeing negative sine x over 1 plus cosine squared x?
Yeah.
Sine squared x.
Not quite.
What? Is it negative?
Uh-huh. So, in terms of, wait, I'm not sure which way you meant that, Caitlin, but it can't be sine squared x because it's off by a negative. Because, are you thinking Pythagorean identity here? The Pythagorean identity you're thinking of is sine squared x plus cosine squared x equals 1. And so this would have to be 1 minus sine squared x, or 1 minus cosine squared x for us to replace it with sine squared.
Wouldn't it just be a negative
Yeah.
sine squared x if you did it like that?
No, then it'd have to be a negative 1 plus cosine squared x.
I was still.
Exactly. It's off, one of these signs has to change on the 1 plus cosine squared x for the Pythagorean identity to work. Okay, so, and yeah, because this is 1 plus cosine squared x, I can't do anything with sine and cosine, do anything fancy there, so we're just stopping there. It's not, some of these are a little uglier, some of them not too bad. So, okay, F. Y equals sine inverse of e to the x. So I'm going to start by thinking about my u. And my u value is the e to the x. Okay. Derivative of sine inverse of something.
1 over the square root of 1 minus e squared.
So 1 over the square root of 1 minus e to the x quantity squared
Times e to the x.
times the derivative of e to the x, which is e to the x. Cleanup wise, if you didn't already put it there, on top, 1 times e to the x is e to the x. In the square root, the square root of 1 minus, what is e to the x quantity squared?
Two either.
Which way did you say it? E to the
2x.
2x. And think of it, first of all, if it's a base and it's a power raised to a power, if it's a power raised to a power, you're multiplying the powers. Or if you're doing e to the x times e to the x, you keep the base the same and add the exponents. Okay? Here's some basic exponent rules there. Okay. It's weird to think that this is example 3. I feel like we've done a lot, but I guess, was that first page 1? It was just example 1, ABC, wasn't it? Okay. Get done? Good. Thank you much. Okay. Number 3. Find an equation of the tangent line to the graph of the function y equals arctan of x over 2 at the point 2 comma pi over 4. Okay, we need the derivative because that's going to provide us with our slope. Okay. So now, one thing it might help you to think about, arctan, of course, you can write as tan inverse. I think that's irrelevant at this point. X over 2. What's another way to think of x over 2 that might be helpful here in a moment? That's 1/2 x, yes? I'm not saying you have to write it like that, but that's going to help in a moment, isn't it? Okay, because when we see x over 2, we're like, I don't know what the derivative of that is. When you see 1/2 x, you guys, oh, perfect, I know that derivative. Okay, so dy dx, derivative of tan inverse of something. Think plus, right?
1 plus
U squared.
Okay, 1 plus u squared, so 1 plus 1/2 x squared times 1/2. Okay, so let's see. On top it's a 1. In my denominator, I guess I'm going to probably take a couple steps to do this. First of all, that 2 is going to be 2 times my entire denominator. 1 plus, oh, I wrote that wrong. Did you guys catch that? It's 1/2 x, but where should that 2 be? That should be on the outside, so my mistake there. What is, I just went to ask you, what is 1/2 x quantity squared?
X squared.
The x part will be x squared.
Oh, this is an
Or 1/4.
What is 1/2 times 1/2?
A 4.
1/4. So this piece is going to become 1/4 x squared, or if you prefer, you could be saying x squared over 4 right now. Okay? Now, if I distribute that 2, 1 over 2 plus, what's 2 times a 4th?
the gap to fit the 1/2 there. Right? What do we do?
This 1/2?
Yeah.
Are you saying I forgot to put it here?
Wait, I don't know.
That's what I moved out here. Okay, sorry. So what I did, 1 times 1 is just 1 on top, right? The 2, I moved out front. What are we doing back there?
He dropped his water bottle, and then I leaned over to look at it, and my book's lit up.
I heard the water bottle. I was like, okay, the water bottle fell. And then I was like, wait a minute, there's more commotion. Okay. 1 times 1 is 1 on top, yes?
Yeah.
And then basically I have this whole piece here, right? That becomes this piece in parentheses here. I cleaned it up. 1 plus 1/2 x squared is 1/4 x squared. This 2 is 2 times that whole denominator. So I just moved it out front. Okay? So my 1/2 is still there, right? Now, we're at 2 times 1 plus 1/4 x squared, so now I took my 2 and I distributed. 2 times 1 is 2. 2 times a 4th x squared is going to be a 1/2 x squared. You won't see an answer like this. You won't see an answer that has a fraction within a fraction. So I'm going to ask you to go one more step. I need this fraction gone, which means I need the denominator of 2 gone. How do we get rid of a denominator of 2? You multiply by 2. If I'm going to multiply the bottom of this big fraction by 2, then guess what? We're going to multiply the top of the big fraction by 2. So now, I'm going to have dy dx is equal to, on top, 1 times 2 is 2. In the denominator, distribute this 2, yes? 2 times 2 is 4, plus 2 times 1/2 x squared is x squared. So it cleaned up quite a bit, yes? Okay, that is my dy dx. Okay, so we had to find the derivative. Derivative was going to allow me to find the slope. So how are we going to find the slope?
The slope?
Well, this is the derivative, which represents the slope of the tangent line.
Yeah, we gotta plug it into the equation.
We need the specific slope at the point 2 comma pi over 4. Because we're trying to write the equation of the tangent line at that specific point. This just represents the general. So I'm going to say this, my slope, whoops, I meant to write m equals, is going to be dy dx evaluated at 2 comma pi over 4. And evaluated at 2 comma pi over 4. It's going to be 2 over 4 plus x squared, so 2 squared. So you end up not using the y in this derivative. That's good since it was a fraction, yes?
Wait, you just take the x and plug it in?
Uh-huh. Officially, you're plugging the x and the y in, but this particular derivative doesn't have any y's, so the y value is irrelevant. Do some math, and you might have a slope that matches mine, right? So, what do we have? A slope of 1/4, a point of 2 comma pi over 4, and we can write our equation. Y equals 1/4 times x minus 2 plus pi over 4. I don't know why I boxed that. I don't normally box things, but I did. I don't normally box things in AP. That's what it is.
Yeah, pre-calc you'd always box.
I do. And I probably haven't, I'm guessing I haven't talked about this. I don't box things as much in AP. And there's various thoughts on it. But sometimes the thoughts is don't box your final answer on a free response. Because if you box it, it's kind of locked into you. You're saying, here's my answer. Grade this. And if you don't box it, then
They can take
there's
whatever you.
there's a little bit more freedom for maybe them to grade. Now, I've heard both sides of this. Okay.
Does it make a difference when you're grading the test?
For me, not necessarily, because I'm a little more lenient and I look at everything if I need to. I mean,
I only box or underline my answer if I'm really confident about it. If I don't know, I just leave it.
and that's the idea here. So, and as I said, I've heard both sides of the argument here. And so that's where, I at one time heard, do not box answers. Do not. Like, that was a very strong statement. But then I've since heard other arguments that says it's not really a big deal either way. So, but it is a thought, So I try to not box answers as much. Yeah. So that's why you see me more like, I feel like I need to do something. Now, here's the thing. On the AP test, do you even really have to do something? I don't know. Not necessarily, I don't think.
If they
But-
wanted you to do something, they'd say it.
True. Okay, example 4. Find dy dx when the tangent of 4x minus y equals 4x. They give us a lovely hint. All trig functions will disappear in your answer. Now, the problem with this one, find dy dx. This would be a lot easier if it was y equals, wouldn't it? But it's not y equals. So, with that in mind, I guess I did make it y equals here, didn't I? I was getting ready to take us implicit differentiation. Okay. And if I did implicit differentiation, we'd still have a trig function there, so that's why the hint
How
is
do
important.
we know that we define inverse here? Or we don't?
Well, okay, so here's what we're going to do. The problem is, this y is in here, right? And so we can either use implicit differentiation, which is going to be rather messy here, or we can get the y out of the tangent. And to get the y out of the tangent, the technique is to, since how do we get rid of a tangent? And to get rid of a tangent, we can take the inverse of it. Basically with the idea that an inverse and a function will cancel each other out.
Could we divide the 4x minus y?
Nope. Because it is the inside of tangent and it's connected to it. So the idea here is we're going to take tangent inverse of both sides. So on the left, it's tangent inverse of tan of 4x minus y. On the right, we're going to do tangent inverse of 4x. Okay. Now, this is a technique. I don't know that it's one we've used before, but by doing the tan inverse of the tangent, okay, the idea is that they are going to essentially cancel each other out. When tan inverse and tan cancel each other out, what are we going to have left? Just the 4x minus y. Now, which is great because we got the tangent out of the left, we can now solve for y. On the right, what did we introduce? We introduced a tangent inverse. Okay? So it's a technique that you can use. Now, with this in mind, in order to differentiate, we need to first solve this equation for y. So if I'm going to solve for y, I'm going to subtract my 4x over. So negative y. And I'm going to write it as negative 4x plus tan inverse of 4x. And we don't want it to be negative y equals, so what do? Multiply by negative 1 or change all your signs. So then I have y is equal to 4x minus tan inverse of 4x. And now we're ready to take the derivative. So derivative of y is dy dx equals, well, he gets to start off easy. What's the derivative of 4x? 4. Minus the derivative of tan inverse of something.
4 over 1 plus 4x squared.
As long as when you say the 4x squared, it's 4x quantity squared. Right? In other words, as long as, did you write your parentheses and the squared on the outside?
Yeah.
Then you're good. Now notice, he put the 4 on top. Or can we do that? Yeah, there's already a 1 there, and basically that's his chain rule. Yes? I'm good with that. Okay. Let's do some cleanup. Cleanup, and we're there. So 4 minus the 4 on top. My denominator is officially 1 plus 16x squared. There's part of me that says leave it here. I mean, it's a derivative. Okay. I'm looking at my answer key, and the answer key got a common denominator and put this together. The idea is, what would the denominator have to be? Yeah. So, because I already have the 1 plus 16x squared, this front part, 4, is going to have to become a denominator of 1 plus 16x squared. So think of it as 4 times, if it's 4 over 1, you want the denominator of 1 plus 16x squared. Oh my gosh, this is messy. I can't. I've got to back up for a moment. Okay, 4 as a fraction is 4 over 1, yes? How do we get a denominator of 1 plus 16x squared? You multiply the denominator by 1 plus 16x squared. If you do that to denominator, what do you do to the numerator? Multiply by 1 plus 16x squared. And then it's still minus the other fraction, which is 4 over 1 plus 16x squared. Did I make sense of what I did there? If we put this all together as one fraction, my denominator is 1 plus 16x squared, right? If I put my top together, I'm going to have to take that 4 on the first piece and distribute it. So it becomes 4 plus 4 times 16x squared is 64x squared. And then minus 4 from the other fraction. And then what little thing will happen here? The 4's cancel. And I have 64x squared divided by 1 plus 16x squared. Okay. You know, we were here. Okay. Those are both good answers. Depends on the scenario. Okay. Seeing it as one fraction is probably more common. Okay, so making that algebra happen. Okay. Continuing along. Let g be the inverse of the function f equals 2 cosine x on the interval from 0 to pi. Find the value of g prime of 1. Now, realize, what was g defined to be? G is the inverse, yes? So when they say find the value of g prime of 1, they're saying find f inverse prime of 1 is what they're saying. Right? I don't know if you guys think better with g's or with f inverses. I don't care which way you think about it. G is the common abbreviation, but so if they want us to find that, you guys remember your inverse function definition from the previous lesson?
1 over of g of x.
F inverse prime of g of x, or g.
So you said 1 over, yes? And then I got lost in what we
I think it's f inverse prime, f prime of g inverse.
Well, it'd just be g. It'd be g or it'd be f
I
inverse.
don't understand
G of x.
F prime of g of x, which my x though is 1. Keep in mind, anytime I say g is another way to say f inverse, right? So if your brain works better thinking, oh, this is really 1 over f prime of f inverse of 1, that's what it is also. Okay? Now, with that in mind, okay, go back to 1 over f prime. We need g of 1, or f inverse of 1.
So do we need to solve 2 cosine x like inverse?
So it'd be the f inverse. Wait.
When you bring the f and the g, I'm lost. Like,
Are you someone that's better if we just stay all with f's?
I don't know. Just like that formula just doesn't click.
Okay. And, huh?
Like I understand the trig stuff, but this I just don't get.
And I will say my brain honestly works better for whatever reason. I struggle when they use the g's. This is a personal thing.
Mhm.
My brain works better with the f inverses,
Mhm.
which is why you see me also often say, okay, this right here is the same thing as this, right?
Mhm.
So we need to find g of 1, which my brain's thinking, okay, I need to find f inverse of 1.
So do you set it equal to 1?
Yes. Because so the idea here is if I need to find f inverse of 1 equals something, remember that is f of something equals 1, right? If I need to find f inverse of 1, or in other words, this is the same thing as saying g of 1, right? I need to find f of what equals 1. So yes, we're going to take 2 cosine x, which is f, and set equal to 1. I'm going to solve for cosine x. So cosine x equals 1/2, right? At what x value is cosine equal to 1/2?
Is this the?
I think it's pi over 3.
Pi over 3. This for me is when my brain, and I don't know, and I'm going to erase this because obviously I'm working in the next problem here, but when my brain, I don't know how you guys have it memorized, but that's what my brain's doing right now. And we're wanting to know when is cosine equal 1/2.
I do 1, 2, 3, 3, 2, 1.
Okay. So we know x is pi over 3 here, yes? With that in mind, okay, this right here, that means what? F of pi over 3 equals 1. So f inverse of 1 is equal to pi over 3. Or you could say g of 1 is equal to pi over 3 as well.
So f prime.
So now it's 1 over f prime of pi over 3.
So we gotta take the derivative of 2 cosine x and plug pi over 3.
Yes. So if f of x is 2 cosine x, then f prime of x is
2.
Wait,
We have to do the
2 sine 2 negative sine x.
I'm going to write it as negative 2 sine x.
Yeah, that makes sense.
Okay. But I mean, you know, your brain was thinking here, I get it. Okay, so the idea just, the coefficient just carries along. What's the derivative of cosine of something? It's negative sine of something. So negative 2 sine x. We were being asked to do what? F prime of pi over 3. So negative 2 times sine of pi over 3. Oh, well, my chart is kind of helpful right now, isn't it? Sine of pi over 3 is, did she say 1/2?
Yeah.
Okay, I'm disagreeing.
Oh, I was thinking pi over 6.
Oh, okay. So I'm doing negative 2. Sine of pi over 3 is square root of 3 over 2. So I end up with
square root of 3.
negative square root of 3.
So g of prime of 1 is
G prime of 1. I have it listed as negative 1 over the negative of 1 over square root of 3. I didn't rationalize. Could you rationalize? Sure, if you remember how, right? It'd become negative square root of 3 over 3 if we rationalized.
Yeah, because you multiply by square root of 3.
Right, you multiply top and bottom by square root of 3, yes? Okay, I'm going to erase my lovely little chart, but that was helpful at the moment, wasn't it? Okay, one more. Number 6. Find the slope-intercept form of the tangent line at pi over 4 negative 1 to the graph of x squared plus x tangent inverse y equals y minus 1. Round to 3 decimal places. That is fun stuff, people. Now, it does mention a calculator. The only advantage I see with the calculator is when it gets to plug-in time, we're going to use the calculator. Okay? I don't know, maybe there's something else I'm missing. There's a way we could use the calculator sooner, but... Okay. This equation is very implicit. X's and Y's are very mixed up. If I'm trying to find slope-intercept form of the tangent line, I need the derivative to find slope, yes? So we are truly using implicit differentiation this time. So derivative of x squared is 2x plus. What do you notice about x tangent inverse y? Did we throw a product rule in here?
Could you, if you wanted to, could you rewrite this equation and like add the 1 over? Might not make a difference.
It's not going to make a difference when I have a y inside my tangent inverse. Okay, so product rule. Derivative of the x is 1 times tangent inverse y. Product rule says plus. Now I'm going to keep the x. What's the derivative of tan inverse of something? Okay, so 1 over 1 plus u squared, and then chain rule times u prime. So 1 over 1 plus y squared times, what's the derivative of y? We have to say times a dy dx. Equals, derivative of y is dy dx minus the derivative of 1, so that is minus 0. Okay, this is why we're going to use the calculator here in a moment. Okay, we need to solve for dy dx. Don't tell me it's already solved for dy dx because I've got 2 dy dx's, yes? So what I'm going to do is I'm going to keep my dy dx on the right, and I'm going to subtract over the other term to join it. Well,
No, you would.
yeah. Okay, so hang with me here. 2x is staying, yes? Plus tan inverse y is staying, yes? Now, realize this x times 1 over 1 plus y squared times dy dx is one term. So it's going as one term. Now, I'm going to, as we move this, what is x times 1 over 1 plus y squared? We make that x over, okay? So now I'm going to say equals. We already have a dy dx on the other side. And now I'm going to subtract the x over 1 plus y squared times dy dx. Did that work for you?
Yes.
Okay. On the right, both terms have a dy dx. What can I do? Factor it out. Are you going to kill me if I flip-flop the sides, or I'll wait and flip-flop them next time, I guess. So I still have 2x plus tan inverse y. If I factor out dy dx, dy dx times, what's dy dx divided by itself? 1 minus x over 1 plus y squared. And then can you write this lovely thing as dy dx equals? Yeah. So I'm going to have dy dx equals, on top is the 2x plus tan inverse y divided by 1 minus x over 1 plus y squared. Nope, I'm stopping here.
What?
Here, wait. Here, okay, wait. The question, it's not. This is not our final answer.
If it was, then no.
If it was, we'd have to do some more manipulating. But the question was to find the slope-intercept form of the tangent line. This is my derivative. Does it matter how messy it is? No, it's just a matter of how messy you want to work with. Well, there's this lovely little calculator symbol over here. So it doesn't matter how messy it is because I'm getting ready to plug this messy thing into my calculator. Do you see what I'm saying?
Mm-hmm.
Okay, now, in order to write slope-intercept form, we're going to need to find the slope.
Yeah.
So we're going to do dy dx evaluated at the ordered pair pi over 4 negative 1. I'm going to go ahead and write it out with it plugged in. But that's, you know. So 2 times pi over 4 plus tan inverse of negative 1 over 1 minus pi over 4 divided by 1 plus negative 1 squared. I mean, yeah, there's some shortcuts and cleanup you can do, but I need to give instruction or you guys are figuring it out.
Exactly.
Tan inverse, you guys know to do second tan, right?
Mm-hmm.
Okay. My answer's on the screen. Did your answer come up with my answer?
Yep.
Okay. So 1.2 through, nope. 1.293260293. Close enough, right? Okay. Final answer. Slope-intercept form, yes? Now, it says slope-intercept form. Do we know our y-intercept? I don't know my y-intercept right now, do I? So,
It's not negative.
no, it's not negative 1 because that's not when x is 0.
Slope-intercept.
Yeah. Now, here's what I would do, though. I mean, slope-intercept form means we're in the end looking for y equals mx plus b, yes? But here's what I would do. Can we start with the form we normally use, that modified point slope form, and then adjust it? In other words, can I go ahead and say y equals, okay, I used 1.293 as my slope. I used a 3 decimals rounded times x minus the pi over 4 and then minus 1. If they didn't ask for point slope-intercept form, I would just stop there. And in all honesty, on AP, normally, they don't ask for, a specific form. So 1.293x, I would do this part on the calculator. You're going to distribute the 1.293, multiply it times the negative pi over 4, and then you're going to subtract 1. Yes? Mine is up on the screen. Rounds to be minus 2.016 if we're sticking with that 3 decimal places. Okay. Here's what I'm going to say. I'm not going to make homework due till Tuesday. Because I'm not going to make you two stress over it, and I don't know what Augie and Tate are doing over the weekend. Because I wasn't very clear yesterday. I said, said if you can, try and look at it. The advantage is the more you get done before Monday, the more time you have to look at the review. Okay, so I have the review ready to hand out on Monday. I would encourage you maybe do some 3.5 over the weekend, but if it's one of those weekends where you just can't, then so be it. Does that make sense?
Mm-hmm.
You do you. That's what I'm saying.